Hello and welcome to the first lecture of part 5. In this lecture, we're going to be talking a little bit more about statistical modeling, and we'll also be reviewing what we have seen in previous lectures. So hopefully all of this will provide you with a little more clarity. Now this table will look familiar to you because, as I've said, we will see it again and again over the course because it's a nice overview of the modeling that we will cover in this course. So in terms of predictors, we're going to be looking at a categorical predictor with a continuous response. And this will, of course, lead to ANOVA, so the analysis of variance. And we've touched on that in previous lectures, and we're going to talk about it a little bit more in today's lecture. Are there any differences among the population means? Now, this is just a very common question. Of course, you're going to, draw a sample from that population and look to see if there is a difference between sample means, but of course you want to generalize. So the big question is there any difference among the population means? In this case, we're going to have a categorical predictor, so that is your group variable. In this case, for instance, has 2 levels, and your response is going to be continuous, so something you measure from a continuous random variable. This will lead to a one-way ANOVA. We've talked about this before. And so another way of asking would be, does information about group membership help predict the level of a numeric response? So how do we ask the research question for a one-way ANOVA? For example, do accountants on average earn more than teachers? Well, this is perfect because this is answerable by yes, no, which is something that you can test using a statistical method. Now, in this case, because accountants are going to be compared to teachers, we only have 2 levels in our group variable. So this would be a good case for a t-test. And as we've mentioned, a t-test is actually a special case of an ANOVA. Now, what if the question was, do people treated with one of 2 new drugs have higher average T-cell counts than people in the control group? In this case, our group variable has 3 levels. So as we've seen before, in this case, we need to perform an ANOVA. And if you remember, we were using proc GLM. Another good example for a one-way ANOVA would be, do people spend different amounts depending on which type of credit card they have? And in this case, you could have as many different credit cards as you would like, and that would represent the different levels of your group variable. So what are the hypotheses used in a one-way ANOVA? Well, you'll remember the null, of course, means that there is no statistical significant difference between the means of your group variable levels. Excuse me. In this case, we're using a fertilizer as your group variable. There are 4 different types of fertilizers, and your outcome is bulb weight in tulips, let's say. Your alternative hypothesis, though, is that a difference would exist, a statistically significant difference would exist between any 2 of your levels. So you have various combinations possible, and in the case of 4 levels in your group variable, you have 6 possible combinations. So don't forget that your alternative hypothesis is just saying there's at least one of those 6 different pairings that could be statistically significant. Here's a nice graphical overview of how ANOVA deals with variability. So if you were to consider the total variability that would exist in bulb weight, because that is our outcome, what it does is it considers 2 big chunks of the variability. The variability between the groups, which is between the levels of your group variable, so the 4 different types of fertilizers, and then it partitions off the variability within the group, so within the bulbs of a given group, or fertilizer, sorry. And so we call this the sums of squares for the model and the sums of squares error, because that's unknown variability. Let's quickly review sums of squares. So you'll remember the overall mean. That's an easy one. You just take all your data points and you divide by the number of data points you have in the sample. You'll remember the total sums of squares is the difference between each data point and the overall mean squared and all summed together. So in this case, 28 with a grand mean of 6. The error sums of squares, a little bit different. You take the difference between the data point and its group mean. So you'll see here for group A, the mean is 4. For group B, it is 8. And so the sums of squares is going to be the difference of the data point for the group minus its group mean squared, and then all of it summed together. And in this case, you have a sums of squares for error of 4. The model sums of squares, in this case, a little bit different. We are just looking at the difference between the group mean and the grand mean, or the overall mean. In this case, for instance, for group A, it's going to be 4, which is the group mean, minus 6, which is the overall mean squared. But in this case, you weight it because there are 3 data points in that group, so you multiply it by 3, plus the other group, which is 8 minus 6 squared, times 3 as well, and so your sums of squares model is 24. Now we've seen the F statistic before when we were comparing the variance between the groups in a t-test, and we wanted to see whether we could use the pooled variance equation for the calculation of the standard error. Now we're using it again here when we're comparing the variability within the model, using the mean sums of squares for model, and we're comparing it to the variability within the groups, and we use the mean sums of square for error. This figure here just shows you the distribution of the F statistic depending on the degrees of freedom. The first number here in your degrees of freedom, so it's F, and in brackets, the degrees of freedom for the model, followed by the degrees of freedom for the sample size. And here are your cut values depending on those degrees of freedom. For if your F statistic is greater than this cut size, then it is considered statistically significant at an alpha of 0.05. So once again, important is the R square, which we call the coefficient of determination. And now that you know how to calculate sums of squares, the R square is simply the sums of squares for model divided by the sums of squares total. And it represents the proportion of variance accounted for by the model, as you guys all know already. This, once again, is how you would write your equation. You guys, once again, we've covered this, but this is just a little refresher. So our example for bulb weight, we have our base level, which is our intercept. We have fertilizer, which is our group variable. And then we have our unaccounted for variation, which is typically called error. The GLM procedure is the one we go to in order to perform our one-way ANOVA. Once again, we have seen this before, but here's a nice little refresher for you. So what are the assumptions for the one-way analysis of variance, or ANOVA? Well, the first one is observations are independent. And we've seen this before when we were looking at the t-test, and we were mentioning that if there was a correlation between the data points of the two groups, that we should perform a paired t-test analysis. In this case, for the ANOVA, it's the same thing, but we're just looking at the possibility of more than two groups. And once again, if there is a relationship between those groups, then we should not be performing a standard ANOVA. The second one is errors are normally distributed. So when we calculated that sums of squares of error, those errors need to be normally distributed. And finally, all groups have equal error variances. Well, we've seen this before once again when we did the t-test and we wanted to see whether the variance between the two groups was the same, was equal. It's the same here in ANOVA. However, we just have possibly more than two groups. And once again, the variance between the groups needs to be the same. Okay, back to our table. Now we're switching it up. The predictor is going to be continuous and the response is going to be continuous. You're going to say, hey, we've seen that before. We have. We've seen it when we did regression or linear regression. It's also called ordinary least squares regression. So when we're looking at two continuous variables, you'll remember that if there is a relationship between the two variables and, for instance, it's positive, then you're going to get this figure where with an increasing in x, you get an increase in y. The dashed red line represents no relationship between the two variables when your slope is 0. So scatter plots are great for having a peek at your data, and this is something I always recommend people do. The very first thing you should do before you do any statistics is to plot your data and just have a look at it. Because what you will see, possibly, is that, oh, I was expecting a linear relationship, but, oh, what's this funny curved look? Well, in this case, for instance, it is a quadratic relationship. Or you may have a cyclical. For instance, if you're looking at fever in children with systemic arthritis, it will be cyclical. And then, of course, this is the, oh, darn, I have to redo the study because there's no relationship.